Okay, this is just going to be a quick minute or a quick video for those of you who were not in class today, or those of you who need to copy the rest of the notes, or just need it to go a little bit slower so you can pause it. So these are the notes that we took in class. I was having iPad issues, so I wasn't able to record the actual lecture, but I'm just going to run through what we took notes over. So this is written in your lab journal, so I would reserve the first 2 pages for your table of contents, and then you can start writing these notes. We only write notes in the journal if it's something that I need you to keep for the entire year, like on hand. So Unit 1, Math and Measurement, is important because you're going to be using it in all your labs, as well as a lot of your calculations that you're going to see this year. So for Math and Measurement, what we started with today was significant figures. So yesterday, you guys did a POGL that kind of showed the different rulers and pointed out how you're always going to be measuring and estimating 1 digit in every single measurement that you have. So you had a ruler that looked like this, that went from 0 to 10. And then you had a ruler that looked like this with little digits all the way down. And so now you're able to say something like 3.2, and you had to estimate that last digit. And when you get even more lines, you do the same thing. Whereas this one, you could only say 3. So that was what we did in the POGL yesterday. And what that led us to for today was that those numbers that you're looking at, when you do that kind of measuring the right way, where you estimate that last digit, you're creating those significant figures. And so now what we're kind of focused on is, if you have data in front of you, how are you going to recognize what are significant figures, what aren't significant figures, as well as how to do the calculations with them. So the first thing that you had to write down was significant figures. The reason we have them is because you can't record better measurements than what the instrument is capable of. So if you don't have that many lines, you can't be a super specific, you can't pretend that you had a super specific device. Okay, you're limited to whatever that device was able to read. So now that we know why we have them, significant figures are, that's what sig figs are. Okay, so sig figs are any non-zero digit number, so any number that's 1 through 9. So for example, if I had the number 13, that has 2 significant figures. If I have 1.453, that has 4 significant figures. And you need to be able to point out how many significant figures and which ones are significant. Next, we have, sorry, let me get rid of those lines real quick. Okay, so next we have zeros are strange, and that's because they have 3 specific rules that you got to follow when you're trying to decide whether a 0 is significant or not. So the first rule that we're going to kind of review right now is going to be that sandwich zeros count. So sandwich zeros are significant. All right, so here we have the number 103. So this is showing you a sandwich 0, meaning a captive 0, or something that's in between 2 non-zero digits. So there are 3 significant figures shown right here. If I have something like 2.003, I'm showing 4 significant figures. So those are those 2 examples. The next thing is leading zeros never count, as in they are not significant. Leading zeros are not significant. So if I have something like if I have 0.00103, this is only showing you 3 significant figures. And that's because these first 3 zeros that are right here, these are placeholders. So if I were to turn around and write this in scientific notation, it makes it a lot more obvious, I would say, because if I were to write it in scientific notation, which I'll go over in just a little bit, it would be 1.03 times 10 to the negative 3. And here you can see that sandwich 0 is there, and there's only 3 significant figures. But these zeros right here, they're just placeholders. We're going to see in the next rule that there's also placeholders that can be at the end, and so placeholders don't really matter in terms of being a significant figure. So leading zeros are not significant. Next, we've got trailing zeros. Trailing zeros are significant only if there is a decimal. So back to that same number, if we throw a couple zeros at the end, we have 0.0010300. This is actually showing you 5 significant figures. These last 2 zeros do count, or they do matter, because there's a decimal here. What it's telling you is that you have a very specific measuring device, and that's where those zeros are coming from, okay? It's very specific. It's a specific measurement. So you have to include those zeros. They do count. Here we have 1,030 with a decimal at the end. This would count as 4 significant figures. If I did not have that decimal at the end, I'd only have 3 significant figures. So, so this is showing you the trailing zeros are only going to count if there is a decimal. So that moves us to our next part, which is using these significant figures. We're going to be doing lots of calculations in chemistry, and so the next section is about sig fig math. So it's split into 2 categories. We either have addition and subtraction or multiplication and division. Let's start with addition and subtraction. We would be using the decimal place rule. Here you would calculate your answer in your calculator. So I put in 350.04 plus 704, and my calculator would tell me this answer, 1054.04. Once I have that, I'm now going to round my answer to reflect the least number of decimal places. So I had to go back to these first couple numbers and look to see how many decimal places there were. So this one has 2 decimal places. This one has 0. This is my least number of decimal places. So therefore, my answer has to have 0 decimal places, meaning nothing after that decimal. So I'm going to take my number. Here is where I'm going to be cutting off. So this is the number that would have to get rounded. I'm going to check the guy behind it, and that means that I'm going to stay at 1054. If this 0 right here was a 5 or 6, 7, 8, 9, I would have rounded this up to a 5. So when you are multiplying and dividing, you're going to be using the significant figure rule, okay? Once again, you're going to calculate your answer. So for this example, I have 20.0 times 0.030. That would give me 0.6 in the calculator. Now I'm going to round my answer to reflect the least number of significant figures. So when I went back to count, this is 1, 2, 3. The trailing zeros count because there's a decimal. This is 3 significant figures. This has 2 significant figures. Therefore, my answer can only have 2 significant figures. But our problem is that we only have 1. So we're going to add a 0 to the end of that, and this would be my final answer. 2 significant figures, 0.60. Another example of that would be 21 times 210. I would have come out to have 4,410 in the calculator. Well, once again, I can only have 2 significant figures because of these numbers. And so I'm going to look over 2 significant figures over, check the one behind it. I would have to round down to 4,400 because now I only have 2 significant figures. So overall, significant figure math runs around the idea of you are only as strong as your weakest link, or you're only as specific as your least specific instrument that you're measuring with. So that's significant figure math. The last thing we covered in class today was scientific notation, and I kind of summarized it that you really only need to know 2 main ideas. First, this right here, this is the layout of what scientific notation looks like. And then I also address the metric system in class. So you'll be using these kilo, milli, centi, deci, all those kinds of prefixes because they're all part of the metric system. And so what the metric system is based around is this 10. So anytime you have the scientific notation times 10 to the something power, it's talking about moving a decimal right or left, right? So here, 1 kilometer is equal to 1 times 10 to the 3rd power meters. What that means is that this decimal that was behind the 1 goes 1, 2, 3 to the right because there's a 3 up here. So it's 1,000 meters, okay? So the two big ideas that I wanted you guys to remember is that if I have a positive exponent, that means it's a big number. A big number is just anything greater than 1. If I have a negative exponent, I have a small number. A small number would be anything less than 1. So if I were to have 1054 and I wanted it to be in scientific notation, I would move that decimal all the way behind the first digit. So I would have you only want one number in front of your decimal when you're writing things in scientific. 1.054 times 10 to the third power. If I were to have had 1,540 with this decimal at the end, I'm saying that this 0 counts. So I would have to have that 0 here. And I would just do the same process to get 1.0540 times 10 to the fourth. On the other end, where we have a small number, if I have something like 0.0030, I would move that decimal until it's behind our first non-zero digit. So then I would be left with 3.0 times 10 to the, I moved it 3 times, and because it's a small number, I put a negative, times 10 to the negative 3. You were also given homework today, so if you were not in class, just make sure you kind of look at the PDF that's posted on Google Classroom. All right, see you Tuesday.